All right, welcome back. So relative frequency distributions. The relative frequency of a class is the fraction or proportion of the total number of data items belonging to a class. So we had this stuff here, right? We're 2, 3. And the relative frequency is 2 out of 20, 3 out of 20, 5 out of 20, 9 out of 20, 1 out of 20. So 2 out of 20 is the same as multiply 2 and multiply 20 by 5, and you get 10 out of 100. So this is 10%. And multiply this one by 5, and it's 15 out of 100, or 0.15, or 15%. And so we could also express all this as a relative frequency, 0.38 and 0.16. So I'm just like checking this out here. Let me just look at this data, and let me grab our data. And our original data is here, and we have 2 out of 20 and 2 out of 20. I'm just bringing this down here, and 2 out of 20. So here's an example where, like, I think the textbook has an error, but let's investigate this together, okay? Whoop, I gotta keep that size apparently. I can't change the size of it. So we'll move this over here. We'll put this up. I don't know where we could put this. We're out of room. We can't have it here. There's not enough room. So relative frequency of a class is the fraction or proportion of total number of data items belonging to a class. So relative frequency of a class is the frequency of the class divided by the total, right? Total number of data items belonging to a class. Relative frequency distribution is a tabular summary of a set of data showing relative frequency for each class. Relative frequency and percent frequency. So let's do that. So here's relative frequency, and then here is percent frequency. There we go. And we'll make these bigger. Select both those, and then double click the bar between the column headers, and that auto sizes it. So this is going to be equal to 2, that reference there, divided by this reference here. And I want to keep that reference absolute. So I press F4 on my keyboard to keep that reference absolute. And when I do that, I get those right there. And I don't want to just autofill it, but I'll go into my formula view and then copy this, Control C, and copy this down. And we could go all the way to there. And you can see that the D7 held absolute, but these here were relative. So relative to where this is, take the number to the left and divide it by D7. And now if I do this, right, and then I could get this one here, the percent frequency, by taking that and multiplying it by 100, because to go from a decimal to a percent, you multiply by 100. And so that's 10%, and I could take this and go up here and try to put a percent on it, but it made it 10,000 or 1,000%, because it again multiplied it by 100. So another way I could do that would just be to copy all of let me go into formula view and then copy all of these, and then come over here, and when I paste these, I want to paste as values so it doesn't change the reference. Let me see if that actually works. So edit, paste, special, paste as formula only. There we go, formula only, and nothing got pasted. So I'm just going to recreate these formulas. So it's going to be that one divided by this one, and then that's going to be absolute. And that's exactly the same, and then Control C and bring this down, and those are exactly the same. And so these will show us the same number, but now when I make these percent up here to get that percent sign, when you do that, the spreadsheet automatically multiplies it by 100. So here's 10%, 15%, 25%, 45%, 5%, and then this one as a percent is 100%, right? So it adds all that up. So that's your relative frequency, that's your percent frequency, and I was just checking that because the textbook has an error here. They have different data, and so if you try to compare this to the previous one, how did they get 5 out of 50? That Sprite, is that what we had for Sprite? 5 out of 50, so that's correct, but Coca-Cola was not correct, and whatever, right? There are errors in the textbook, and there is one. But that's how you do it. That's how you calculate it. So that's what that slide there shows you, and how you get the percent frequency, right? Multiplied by 100, and then there's the spreadsheet, and then here's how there's a little bit of information about doing it in Excel if you want to pause the video and look at that. So the next thing we're going to look at with descriptive statistics is a bar chart. This is a bar chart. in Microsoft Excel or other spreadsheets, they call it a column chart, and a bar chart is the one that goes horizontal. But, you know, and so just to illustrate that, if I wanted to graph this, I want to graph that stuff right there. So you select your data, you select your row heading, and you select your column heading, and then you go up to, I don't know, insert, and they call them charts, so insert chart. And then if I come in here to chart, this is known as a column chart. So if I come over here, you can see it's called a column chart, right? But I also have a bar chart. And so here's the bar chart. So a bar chart is, you know, in spreadsheets, horizontal, and a column chart in spreadsheets, which is right here, is vertical. But in statistics, in this textbook, they call it just a column chart. And or they call it a bar chart. They call this a bar chart, even though in spreadsheets they call it a column chart. And you know what? Through most of math, going through high school, we called this graphs. We call these graphs. So that's kind of interesting. But it's kind of interesting to realize that ultimately, at the end of the day, it doesn't matter like what people call stuff or how they, you know, what matters is can you convey the information and can you do stuff. Right? I don't care what you call it, bar chart, column chart, histogram, like can you make it so that we can see it? So a bar chart is, and it's also kind of interesting just to see the inconsistency in the adult world. So a bar chart's a graphical display for depicting categorical data, right? So this shows us here like 2 liked Coke, you know, and it's very easy to visually assimilate this material. Visually, we could really see Pepsi, right? Like Pepsi's really ruling it here. You know, like wow, they're leaps and bounds above everybody else by this column chart. We could also put in a chart that's a bar chart. And so here, if we come down here to chart and we create another one, so let me just create another one. And it looks like it maybe put one back here. So now we've got 2. So I'm going to maybe click these dots and publish chart, move to own sheet. So now it's in its own sheet. But I could still edit this, so edit chart up here, and instead of a column chart, I could go with like a pie chart, right? So here's a pie chart, and then I could add labels to it. So customization, label frequency, I don't know, label sheet 1, 2, label frequency, and I'm just looking for frequency, label, sheet 2, frequency, switch rows, use 1, rows headers. Sometimes it takes a little banging around to get it to show what you want. So legend, chart title and axes, pie slice, Coca-Cola, color, pie chart. I don't know how to get the labels to come out. So I'm not going to take the time to figure it out. Hang on, I'm going to pause the video for 1 second. I'll figure it out. All right, I'm back to recording, and I'm just making sure I'm recording by watching this little thing go up and making sure I have volume. Sweet. So what I did is I went to chart setup. I went to setup, and then I said, hey, what about this one? And I chose this one up here because it had some labels versus I tried to go back to that one. I don't know if I originally had that one, but now I click that and I've got these labels out here. Maybe those are always there and I just overlooked them. And this is where with statistics and with descriptive statistics and with creating pie charts, this is where the phrase that there are 3 types of lies in the world. There are lies, there are damn lies, and there is statistics. There are statistics. And so that's, so grammatically, just to correct that subject verb, there are lies. So are is plural, the plural verb to go with lies, which is plural. There are damn lies, and so are goes with lies there again, plural verb for plural, that subject verb agreement. And then there are also, and then I said there are statistics, and I corrected that thinking it was is statistics, but statistics is plural, so it should be there are statistics. So there's 3 types of lies: lies, damn lies, and statistics. And this is where that phrase comes from, because you could present data in all kinds of ways. Like I could have data and it tells one story this way. I could have data and it tells another story this way. This is harder to kind of tell. That, you know, when you look at this, it's harder to see that Pepsi has this huge market share, these all actually look even, right? And so here everything is actually 16.7%. So this is actually messed up. I'm going to go back and I'm going to delete this one, and we're going to recreate this one, and we'll recreate that and get this up here. And we're just going to select that stuff. And then we're going to go to insert, and we're going to go to chart. And we have a new chart here, and I'm going to make this first one smaller. We'll just keep this all on the same page. So I'll make that smaller like that, and then we'll bring this one over here, and we'll make it smaller, and we'll change its type. And so we want it to be a pie chart. So I'm going to select pie chart there. And so this shows Dr. Pepper's 25%, right? It tells a slightly different story. So let me move this one over a little bit more, and move this one over. And you can see here the different stories that this tells. And so that you could have a descriptive statistic, a chart, and it could tell different stories. So I'm going to choose this drop down arrow here and choose edit chart, and brings this up. And if I want to change, so those labels are a little bit more clear here. And you could kind of say, which way does it seem like, if we're presenting this and we're Pepsi, which way does it seem like we're really dominating? And I could present the data to show that, like, look, Pepsi's really dominating the market. But if we're Coke, can I de-emphasize Pepsi and emphasize us? So let's explore that for a second. But if I come over here to customize and I go to pie chart, and then, slice label here, I'm going to go to the label, and it puts some labels there. So that tells a different story. It makes it a little bit, a little bit different, right? Makes it a little bit different. And then I could come back over here to the setup if I wanted, and so I could copy this, and I can make, well, I guess we'll leave that the size it is. I'll just copy it, Control C, and then we'll put it down here. Copy this, Control C, and then paste, Control V. So now we have another one here, and then I'll go to this one here, and I'll choose Edit Chart, and I could go to Chart, and I could change it to like a 3D chart, and then I could rotate this. So somewhere in here, there's an option to rotate, and Legend, Chart, and Axis Titles, and Pie Slice, and Pie Chart, and Label, Text Color. And so let me pause this and figure out how to rotate it. Hold on. All right, I'm recording again, and I can't figure out how to rotate, but in Microsoft Excel, it's really easy to rotate, and you could like put Pepsi in back, you could put Coca-Cola up in front, and that would make Coca-Cola seem larger than it actually is, and to de-emphasize Pepsi. And you could change the angle. So you could really kind of change the amount of green which is being shown on screen by putting it in back, changing the angle of this 3D pie chart, and bringing Coca-Cola to the front, so you could de-emphasize Pepsi and more strongly emphasize Coca-Cola and tell a different story. Statistics, lies, damn lies, and statistics. So that's where that phrase comes from. All right, so we learned about a bar chart, and you could pause the video and you could read this. I guess I'll just skim through it with you. On one axis, we specify the labels that are used for each of the classes. So here's Coca-Cola, Diet Coke, Dr. Pepper, Pepsi, Sprite. Those are the labels used for this axis. Is a soft drink is the label, and frequency is the label for this axis. And we could have a frequency, relative frequency, and percent frequency scale can be used on an axis. And using a bar fixed width drawn above each class label. So these are the class labels. Sorry, I said that they were the axes things earlier, but it's class label, right? So we extend the height to the appropriate level, and bars are separated to emphasize the fact that each class is separate. So we'll see something which is really like a bar chart. It's called a histogram, but all of the columns are right next to each other, and that's more to show some sort of distribution of data, that is more continuous. But a histogram and a bar chart, this column chart, are pretty much the same thing, except there's no space between the columns in a histogram. And having space between the columns allows you to see that these are different, like separate sort of categories or classes that are being used. So there's your bar chart, column chart right there. And so to do that in Excel, you just saw me do it in Google Sheets, which is a different spreadsheet. But you can pause the video here to see how to do it in Excel. And you can pause the video here to see how to do it in Excel. And now we're going to, I guess this is still you know, that's still Excel there. And so here's a pie chart. And we saw how to create a pie chart too. You can pause the video and you can take a look at that. And so there's another pie chart with the incorrect data right there from the data that they gave us. And then here's another pie chart, you know, that kind of interprets that for you. So you could pause the video and you could read through that. You know, same pie chart, but you could pause the video and read through that. And so that's qualitative data: bar chart, pie chart, frequency distribution, relative frequency distribution, right? So we had frequency distribution, relative frequency distribution, and percent frequency distribution, bar chart, pie chart. That's for qualitative data, right? For categories, categorical data for different classes. So for quantitative data, for data that's, remember our acronym, NOIR, qualitative categorical would be nominal and ordinal, and quantitative would be interval and ratio, right? So and that's numeric. And so for quantitative data, we could also use frequency distribution, relative frequency, and percent frequency distributions. But we could also, we could also do like bar charts and pie charts, like depending upon what we're dealing with. But then we also have dot plots and histograms. So here's histograms. It's like a bar chart, but there's no spaces between the columns. And we have a cumulative distribution, and we have stem and leaf displays. We'll take a look at those coming up. So here's an example. Pause the video, read through it, and here, you know, here's the time it took to do an audit for each of the clients. 20 clients, how many days it took for each client to do the audit. And so to do a frequency distribution, we have to determine the number of categories or classes that we want this quantitative data to fall in. These aren't predetermined classes. Like with soda, we had predetermined classes, right? So right now we are on slide what? We're on slide 23. But with soda, we had predetermined classes. So I'm just looking for my soda data. Where is my soda data? Soda data, is this it? So the different classes are what are people bringing home in their grocery cart, right? Predetermined classes. But with this data, we don't have predetermined classes, right? So we have to decide how many classes do we want, and how wide do we want those classes to be. And so ultimately, our data is going to end up looking something like this. How many did it take 10 to 14 days? How many did it take 15 to 19 days? How many did it take 20 to 24 days, 25 to 29, 30 to 34? Ultimately, our data is going to look like that for our frequency distribution, but we have to create the classes. So to create the classes, when we have this kind of data, this kind of quantitative data, to create the classes, determine the number of classes that you want. Determine the width of each classes, how wide. Determine the class limits. What's the high point? What's the low point? And so the best practice is to have 5 to 20 classes. And data sets with larger number of elements usually require a larger number of classes. So here we only have 20 elements, right, that are being measured. We've got observations on 20 elements. And so here, you know, we're going to use closer to 5 classes. Data sets with larger number of elements would require a larger number of classes. Smaller data sets require fewer classes. The goal is to use enough classes to show the variation in the data, but not so many classes that some contain only a few data items. So use classes of equal width. That's another thing, right? Like it'd be totally confusing if we were like 10 to 14, 15 to 25, 25 to 34. There are different widths, so it wouldn't really give us a sense of consistency as we are talking about describing the statistics we've gathered, right? We want to do it in a way that consistently kind of conveys accurate information. Though if you wanted to mislead people, then that could be a way where you kind of push the boundaries a little bit. So what do we do? Right here, use classes of equal width. So approximate class width would be largest value minus smallest value divided by the number of classes. So here, if our largest value is, where's our data? Our largest value is, I don't know, we got a 33, and our smallest value is we have a 12. So I'm just looking to see if there are any smaller ones. 12 to 33 is 21. And if we want 5 classes, we would have like 21 divided by 5 would be 4. So 12, 10 to 14, 15, 16, 17, 18, 15 to 18, 19 to, right? And so that would be like 10 to 14, 15 to 19, 20 to 25, 25 to 29, 30, 34. Like that's how those 5 classes got created, and that's like a really, mathematical statistician kind of way to describe how to do it, but you just intuitively could kind of like be like, how many classes, how wide should they be? What's my highest data value? What's my lowest? How wide should they be? But this is the mathematical way to express that logic, which I just articulated verbally. So making the classes the same width reduces the chance of inappropriate interpretations. In practice, the number of classes and the appropriate class width are determined by trial and error. Once a possible number of classes is chosen, the appropriate class width is found. And the process can be repeated for a different number of classes. Ultimately, the analyst uses judgment to determine the combination of the number of classes and class width that provides the best frequency distribution for summarizing the data. So as a statistician, right? Like you are determining in descriptive statistics, you got your statistics, how do you describe them to people? You're determining how they get described. You're determining how they get conveyed. Bar chart, pie chart, frequency distribution, relative frequency distribution, percent frequency distribution, right? Putting together different classes, how many classes should there be, how wide should those classes be? Like that's all like, okay, I got to figure that out, how to best convey this message. And so these are the, guidelines for helping determine the classes. You can pause the video and you can read through this. And we should, put this into ChatGPT because I don't know what that means actually, what the textbook's getting at there. What my textbook says this. My textbook presentation says this. What does open-end class mean when putting together a frequency distribution for data like this? Excuse me. That was funny. My glasses came down. So I'm going to get the data. And again, by you seeing me do this, right, and you seeing that I don't know everything, that and how I find the answers, that empowers you to, one, just be like, approach the world in just a more like find the solution kind of an attitude, which employers really love. Like, man, I don't know everything, but I know how to figure a lot of stuff out. If I don't know something, I admit it and I go figure it out. An employer is going to love that. An employer doesn't want somebody sitting there for 2 weeks or 3 weeks or 3 months, like thinking they know, pretending and presenting as if they know how to do stuff in a panic, not knowing how to do stuff and just wasting time for 3 months. Like an employer does not want that. An employer wants somebody who's like, I don't know what's going on. I've tried to find the answer. This is what I've done. What are your thoughts on it? It's super important, that level of humility and results orientation. So you seeing that here, I'm modeling that for you, and all too often because people are caught in their egos, no ego amigo, because people are caught in their egos, that doesn't get modeled. That doesn't get modeled, and it's super important. So you're seeing me emphasize that, like how to find the solution, how to admit when I don't know, and not being freaked out about it at all. And you're also seeing me how to use ChatGPT to find the answer. So let's see what ChatGPT comes up with. Yeah, we'll give it a second. I'll pause the video maybe while it's thinking about it, or come on, baby. Here we go. An open-end class in a frequency distribution is a class that does not have a defined boundary on one side. This typically happens at lower or upper end of data set where it's more practical or necessary to group all data values beyond a certain point into one class. When creating a frequency distribution for this data, you might decide to group the data into classes, and you might set something up like this. So this is an open end. So that makes sense, right? That makes sense. As soon as I see it, I'm like, cool. And why use an open-end class? Outliers, you should know this word. An outlier is a data point that is like really, you got your measure of central tendency, you got the data around it. There's not too much dispersion, but then there's this one point way out here. That's an outlier, right? So open-ended class would be great for an outlier. And, you can read the rest of this here. So there's the first part. You can pause the video and read the first part right there. And then here's the second part. You can pause the video and you can read it right there. You'll learn some good stuff. All right, so that's open-ended, and that was on this slide. And then frequency distribution. In some cases, we want to know the midpoints of the classes in a frequency distribution. The class midpoint is the value halfway between the lower and upper class limits. So here's an example of doing all that. We've talked through all this. You can pause the video. You could read it. And then here's the relative frequency distribution. So we have 4, and to get this total to 100, you multiply by 5. So if you multiply this by 5, you have to multiply each of these by 5. So this would be the same as 20 out of 100, and 40 out of 100, and 25 out of 100, and 10 out of 100, and 5 out of 100. And so we should have like, what, 20, 40, 25, 20, 40, 25, 10, and 5. And so there's the relative frequency, and then here's the percent frequency. These are the percentages, right? So that's how we got that, and relative and percent. And so you could read this, and this is the interpretation of this data. You could pause the video and read that. And here's a dot plot. So moving on to another way, and so this is the exact same data. So we did have one data point that's out here at like 33. And if you remember, here's our data, and we have this one data point that's at 33. And so another way to visually represent the data, right, we could represent it like this, and we could say, oh, okay, that's cool. We could also do this dot plot. And again, this is descriptive statistics. So we're finding different ways to describe what's going on with our statistics. I'm just checking to make sure I'm still recording. I'll have my new computer soon, and I won't have to worry about my video card crashing. But dot plot's another way that we can, hold on. A dot plot's another way we could, you know, present our data to describe our statistics, descriptive statistics. And so that's what this looks like. For each data point, we're putting a dot. And if there's 2 data points at 15, or 2 data points at 14, or 16, 17, or 3 data points at 18, 3 data points at 18, 1, 2, right? So, oh, and here's 3. So they're kind of at an angle. 1, 2, 3. So 3 data points at 18, right? Like this dot plot shows us where our data is. And so that's kind of nice. And it shows us the dispersion, the variance, you know? So we don't have our measure of central tendency here, but we could easily calculate the mean. We could see where the mean is. And so, you know, that might be kind of fun. What is the mean for that data? 19.25, okay? So the mean for that data is 19.25. So our mean is right here. So that's like right here is our mean. Okay, it's like right there. Or we'll put it right here. That's like our mean is like right there, just a little bit past 19. And so based upon this measure of central tendency right here, right, we could see the dispersion of our data. We could see the variance of our data. And so that's kind of cool. It shows you the measure of central tendency, and it also shows you the dispersion or the variance of the data. So done with this one, moving on to the next concept, we could create histograms. So here's a histogram. And so we could take this same data here, right, 2, 20, 40, 25, 10, and we could, you know, do the frequency here. So here we have 4 were measured, here we have 8 were measured, here we have 5 were measured, here we have 2 were measured, here we have 1 was measured. And these are just put right together to show that, you know, even though these are separate classes for whatever reason, a histogram has no spaces between the columns in this bar chart. And it's intended to show that there's more continuation between the data. And so here you can see there's more continuation between the data, right? So that's kind of what a histogram is showing. And so you can pause the video and you could read through this, and you could create a histogram. Rectangle is drawn above each class interval with its height corresponding to the interval's frequency, relative frequency, or percent frequency. So you could create a histogram with any of those, and this one is with frequency, and you can see that on the x-axis right there. And unlike a bar graph, a histogram has no natural separation between rectangles of adjacent classes. So with histograms, you know, we could, and with all data, we could look at the skewness of the data. So this is symmetric, and this is different data. Okay, this is no longer this data here or this data here. We're just looking at skewness, and we're just seeing different shapes that a histogram has. So let's say we had some data, and this was the shape. It was more of a normal bell curve. Okay, it looks kind of like a curve up and down, a bell. You can picture a bell, right, that you ring. That might be hanging from a church steeple, right? It's got its top, and then it's got its wide bottom. It's got its top, and it's symmetric on both sides. This is a symmetric histogram. The data is not skewed, it's symmetric. This is skewed left, right? Like we got data stretching out to the left, it's skewed left. And so an example would be exam scores. There's going to be more C's, B's, and A's than really low scores. Here is data that is skewed right. Housing values. There's going to be more stuff down here at the moderate prices and less expensive mansions out there. It's skewed right. And then here's data that is really skewed right. Executive salaries. So some people have really high salaries. Most people have the salary here. So the main thing here is symmetric, skewed left, skewed right, really skewed right. So that's data that's skewed. Just again, how do we describe the data? How do we talk about it? Oh, that data is skewed left. That data is skewed right. That data is really skewed right. Oh, that data is symmetric. Again, describing statistics. We're just learning to talk about statistics and how do we present them? How do we talk about them? How do we describe them? Symmetric, skewed left, skewed right, skewed right. Okay? That's talking about statistics. And then we have cumulative distributions. Cumulative frequency, cumulative relative frequency, cumulative percent frequency. So here again, we're looking at this data for, I don't know, what was it? Like how many days did an audit take? This data here. And with this data here, we had like, you know, this result here, 48521, which turned out to be 20, 40, 25, 10, 5. And then back to this data here, right, we could do cumulative. 4 plus 8 is 12. 12 plus 5 is 17. So if I get this slide up here with the data, right, so let me get the data, Control C, and then bring this here. I'll just get this data here. Control C, let me get this whole thing. Control C, and then bring this down here and put this here. Control V, and then just bring this up over here like this. And I'll put that right there. And then take this and make it smaller. Control A to select it all and just make this smaller. And then bring this over. There we go. All right, that's pretty good. And we might be able to bring this down, just get it all to fit. All right, I like it. So cumulative frequency, right? 10 to 14, less than or equal to 14 days. 4. Less than or equal to 19 days. How many are less than or equal to 19 days? The 8 and the 4, which is 12. Less than 24 days. How many are less than 24 days? The 5, the 8, and the 4. 5 and 8 is 13, plus 4 is 17. 17. How many are less than 29 days? Here's 29, so it's going to be we had 17 in the last one, plus 2 more is 19. How many are less than 34 days? 19 plus 1 more, less than 34, is going to be 20. Right? So it's cumulative, right? Showing how many are less than this amount. And we could also do the cumulative relative frequency, and if we got that data, it'd work the same way, okay? Or you could just be here, 5 times 20 is 100, 5 times 12 is 60, 5 times 20 is 100, 5 times 17 is 85, 5 times 19 is 0.95. So that's another way you could look at it. And you can pause the video and you could read through this right here. All right, so the next thing is a stem and leaf display. So stem and leaf display, again, is going to show us sort of like how our data is arranged, because we're not only interested in the measure of central tendency, we're also interested in what does that data look like. I've shot a bunch of arrows at a target. Where did those arrows hit? You know, what does that look like? And so we saw that, you know, a dot plot was really good for kind of giving us a visual eye on what our data looks like, the dispersion of our data, the variance of our data. So this was the measure of central tendency right there where my cursor is at 1925, and we could see how data is dispersed or how much it varies around that measure of central tendency. And then when we come down here, right, this is another way we could start to see what is the distribution of our data. And so for this data here, this data would be coming from right here. And so we have 69, we have 68. And so in the 60s, we have 69. In the 60s, we have 68. So this is like the, you know, the 10s, and this is the 1s. So we had 2 figures that were in the 60s. In the 70s, we had 72, 73, 76, 73, 76, 75. And if you look up here, those numbers would be up here. But that's how you do a stem and leaf display. And in this case, this is called the stem right here on the left, and this is called the leaf right here on the right. And you could see the distribution of the data. And so you could see here that like in the 90s, we had the most observations ever. And you can also see that this has kind of a normal distribution, a bell-shaped distribution, where we've got some low ends down here and down here, but then we've got more data as we get towards the middle here, right? So we're going to have data that has what we call a normal, more of a normal distribution, more of a bell curve distribution. That's how you talk about it in statistics. But the stem and leaf display gives us another way to sort of visualize the dispersion of our data. So stem and leaf display shows both the rank, order, and shape of the distribution of the data. Similar to a histogram on its side, but it has the advantage of showing the actual data values. The first digits of each data item are arranged to the left of the vertical line. To the right of the vertical line, we record the last digit for each item in rank order. Each line in the display is referred to as a stem. Each digit on a stem is a leaf. So this is the stem. These are the leaves out here. The number of questions answered correctly on an aptitude test by 50 students. The relevant data is given in the following table. So here it is, and that's how you interpret it. And here's where you can see it's the stem and the leaf, just so you get a visual on it. And you can stretch it out, right? So here, again, there's lies, damn lies, and statistics. And now we're starting to get a different shape, exact same data. But we kind of said, hey, 72, 33, 75, 76, 76. We're stretching out the 7s, the 8s, the 9s, the 10s, the 11s, the 12s, but not the 13, 14s, and 6s. And that gives us a really different shape. So just like the way data is presented tells a story. It's the story that the person who created the information wants you to read. So you have to learn to read between the lines. What story are they telling? What are their motives? And that gives you an ability to make better sense of the world. If we believe the original stem and leaf display has condensed the data too much, we can stretch the display vertically by using 2 stems for each leading digit. Whenever a stem value is stated twice, the first value corresponds to leaf values of 0 to 4, and the second value corresponds to leaf values of 5 to 9. So we split it up in half, right? Just making sure I'm still recording. Good, and our volume, it's all good. Whenever a stem value is stated twice, the first value corresponds to 0 to 4 and 5 to 9. There we go. So there's just another picture of that. And same thing. And then here we have, what do we have? We could have a leaf unit of 0.01. So this is going to be 8.6 and 8.8, right? So this is the stem on the left, this is the leaf, and the leaf is equal to a decimal. So this would be 9.1 and 9.4. So here's 9.1 and 9.4. There are those data values. So you could create a stem and leaf with decimal leaves. And so here, you know, this is just explaining this idea that your leaf unit could be a different unit. So explaining that a little bit further, you could read that. And then here's a leaf unit where it's equal to 10. So this is going to be 1682, right? But we're just saying 1680, right? So the leaf unit, this is 80. This would be 1710, and that corresponds to 1717. So we're just dropping this last digit as insignificant and just kind of like saying, hey, we're dealing here in the hundreds. And so we're just making our leaf unit worth 10. So that's another way to do it. All right, we're going to create a third video here. And in the third video, we're going to go through the second part of chapter 2, 27 slides. But I think the second part goes quicker. See you in the next video.